So me and Monica joke about how he just takes all the money for himself. Is he really?
So, the topic of today's lesson is the rational zero theorem. Since it has a particular name, it probably is important. Before we dive into the definition of what the rational zero theorem is, I just sort of want to review what we did yesterday. One of your exercise questions from yesterday. So let's say exercise from yesterday. I just pulled this question straight from the homework. Right. So one of your homework questions was find all real zeros of f of x equals x cubed minus x squared minus 11x plus 15. So this was on last night's assignment. Now, to find the zeros is to set the equation equal to 0 and solve it. Well, this is a cubic function. It has 4 terms. The technique that we typically use to solve 4-term polynomials is factor by grouping. But the problem was this guy isn't groupable. If you try to group the first two and the last two together, you'll find out that there's nothing you can pull out. So this wouldn't have worked. So this would have been a, quote, impossible or, quote, hard question if it was not for this extra piece of information. Find all real zeros of f of x given that x equals 3 is a 0. So all of yesterday, they gave you a lifeline. Hey, solve this hard question, but we're going to get you started. Hey, x equals 3 is a 0. So the logic was we applied this thing called synthetic division on that number 3, apply to the function. So the coefficients are at 1, -1, -11, and 15. And the idea is that if they tell you it's a 0, it should divide it nicely and neatly. In other words, there's no remainders. So I'm going to fast forward through synthetic division. I had a feeling that everyone pretty much got that, so I'm not going to explain synthetic division. So that's a 1, that's a 3, that's a 2, 6, -5, -15, and we get a 0 remainder as expected. So these coefficients here, down here, represent an x squared plus 2x minus 5. And since the original instruction said solve for the zeros, all you had to do was set the equal to 0 and solve. And then notice it's a regular quadratic, so we didn't have to do anything fancy. Just use your quadratic knowledge. Factor if possible, quadratic formula if it's not, or completing the square. In this case, this guy was not factorable, so we had to turn to completing square or quadratic formula. I'm not going to go ahead and solve it, but that was just the idea of yesterday's lesson. Right. Yeah, you would probably use quadratic formula. I would probably use completing the square because the middle term is even. But, to each their own. So this was an easy problem because, again, they gave us a lifeline. The original function was not factorable, but hey, I don't care. They gave me a lifeline. I'm going to synthetically divide it out and solve it. What today's lesson is all about is, what if we yank that lifeline away? What if they didn't tell us that x equals 3 was a 0? Well, if I were to do the same problem, okay, solve this guy. I know that I have to synthetically divide something out. Well, think about this. If they didn't give you a lifeline, you have to guess what the right number is. And that's not too bad. I'm feeling lucky. Okay, I'm going to guess the right number. Let's do some math here. So I have to guess one right number out of all of the numbers in the universe. I like those odds. That's why I don't make any money gambling. Those odds actually suck. That's a one right number out of an infinite number of possible answers. That's mathematically a probability of 0. So blindly guessing the right x-intercept, blindly guessing the 0 is actually a pretty difficult thing. Fortunately, we have this thing called the rational zero theorem. So that is the job of the rational zero theorem, is to improve our odds on blindly guessing that correct x-intercept. So this is the statement. If f of x equals, and I'll write out the full polynomial definition, if f of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus 1 power plus ... so on and so forth, plus a sub 1x plus a sub naught. If that guy has a rational 0, it will be of the form x equals p over q. Now those letters mean nothing because in the definition, where's p? Where's q? I didn't even use those letters. Well, here are the definitions. P is a factor of a sub naught, which is the constant. It's that very last number. Q is a factor of a sub n, which is the leading coefficient. It's the first number. So what this theorem does is it doesn't solve it for you. I want to make that clear. It's not the quadratic formula. It doesn't give you answers, but rather it shrinks the pool of possible guesses that you need to do. So instead of going from guessing one number out of an infinite amount, which the probability of that happening is very, 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 very low, into guessing one number out of 20, one number out of 10, so on and so forth, it dramatically increases your odds of guessing that right initial number. The best way, I think, to see a definition or a theorem in action is to take a look at an example. So let's take a look at this example here. Suppose I asked you to factor f of x equals 2x cubes plus x squares minus 13x's plus 6, and hence find all real zeros. Well, the first thing I always try to do when they give me a factoring problem is try to be sneaky. Hey, are they trying to throw a fast one by us? Hey, it's 4 terms. Let's see if I can group them. But try as you might. Gosh darn it. Nothing I can factor out. So this guy is not groupable. So this is like the beginning exercise. We have a non-factorable quadratic. I'll put non-factorable in quotes. We have a non-factorable cubic, and I don't have a lifeline. This is what the rational zero theorem states. Your very last number will be your source of p-values. The very first number is the source of q-values. What you want to do, p equals 6, is find all the factors. So what I like to do is that pairwise factoring that we did when we did with quadratics. So start with 1 in the number and then move up to 2. Does 2 divide into 6? Sure does. And that's the entire list. Pairwise factor the q number, which is 2. That's pretty simple. 1 and 2. Okay. So your list, notice what the theorem says. It's p divided by q. Your list is every single possible fraction you can make by taking a p number and dividing the q number. I like to do this systematically one at a time. I like to divide all the p numbers by one q number at a time. So let's start with q equals 1. Well, that's simple. 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1. The thing is, though, these guys are factors, right? And factors can be both positive or negative. If 2 divides into 6, then certainly negative 2 divides into 6. So when I write down my list, I have to make sure I include the positive and the negative. So let's do this. Let's divide every p number by the q equals 1. So 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 6 divided by 1 is 6. I divided all the p numbers by 1. Just do the same thing with 2. Divide all the p numbers by 2. 1 divided by 2 is 1/2. 2 divided by 2 is 1. Wait a minute, I've already written down a 1 here, so I don't need to double write it. You don't need to double write. So the rule of thumb is, when you're making this list, if the p and q share a common factor, you don't have to write them down, because when you reduce them, he'll already be on your list. So 2 divided by 2, I will skip, because I can reduce it. 3 divided by 2, I'll add. 6 divided by 2, I will skip, because we can reduce it. So I've exhausted all q values. Those are my numbers. That's my entire list. So it's still a lot of numbers. I have 1, 2, 3, 4, 5, 6. We have 12 numbers altogether. But hey, I would rather get a 1 out of 12 chance rather than a 1 out of infinity chance. So just like with yesterday, we're going to synthetically divide. The only difference is we are less than confident about what we're going to synthetically divide. And I hate to say this, there really is no skill involved. It is purely just blind luck. Guess and check. So take a look at my example sheet. I did not do the solutions. I don't know what the right answer is. So you guys just spat out some numbers from this list. 0 is not on this list. Negative 2 I heard. So let's just guess. It might be right, it might be wrong. We don't know until we try. So 2, negative 4, negative 3, positive 6. That's going to be a negative 7. That's a positive 14. So you see here how the remainder was not 0. So all this work tells me that negative 2 does not work. So try again. So when you're doing this on your own, I suggest we have like scratch paper or maybe a whiteboard because you might have to do a lot of erasing. So for our notes, I would advise you just hold off until we get one correct. So negative 2 didn't work. Try again. 4. 4 is not on the list. 3. Oh, so someone wants to live life on the edge and use a fraction.
We have to try.
So 3 halves.
Am I gonna do what you said?
2. 3 halves is 3. 4. That's a 6. That's a negative 7. That's a negative 21. Already we can tell it's not going to work. So 3 halves is out of the question.
Negative 3.
Negative 3 I heard. So that's a 2. Negative 6. Negative 5. 15. That's a 2. Negative 6. 0. So negative 3 works. Now recall that synthetic division will reduce your polynomials by 1 degree. So we started with x cubed, so these coefficients would be 2x squared minus 5x's plus 2. Notice it's a regular quadratic. The moment it's a regular quadratic, you don't need to do anything fancy. No more p's and q's. Just go back to your good old quadratic knowledge. The instruction said factor, so I'm going to try to factor this guy. So that's a 2x and x. And it's a minus 2 on the right, minus 1 on the left. Right. A common mistake students make is you guys get so focused, this is a quiz and a test. All right, I got a solution, so I'm going to circle it and move on. That would be incorrect. This right here is the factored form of this polynomial, but the original question is this guy. So what's missing? You have to remember that all of this work here says that x equals negative 3 is a 0. That's what your guess and check found out. So we apply the factor theorem that says if x equals negative 3 is a 0, then x plus 3 is a factor. So you just have to, in your final answer, you have to f of x equals the quadratic factor that you found, 2, and you just have to incorporate the one that you guessed correctly. Right. That would be the factored form of the, quote, unfactorable cubic. And then, of course, once you have it in factored form, it's very easy to find the zeros. The first one is 1/2. The second one is a 2. The third one is that negative 3 that we found out. Right. Easy peasy. So the rational zero theorem is sort of like the tool you would use if you ever ran across a, quote, unfactorable polynomial. So right now, unfactorable should no longer be in our vocabulary. We should be able to factorize it if it has rational zeros. Questions on this example? That is the only idea, the only concept for today's section. I did prepare one other example just to highlight 3 different things. So this example here, I chose for a reason to point out 3 different aspects. So one last example. Let's not do the fact, let's just straight up solve. So find all zeros of f of x equals x to the 4th minus 5x squares minus 5x cubed, excuse me, minus 5x squares plus 23x's plus 10. All right. So I hinted I chose this example for 3 reasons. Reason number 1, okay, he's not factorable, so I'll do my P's and Q's. Observe, my Q value is 1. Well, I don't need to factorize 1 because it's just 1. So I'm always going to be dividing by 1, which means my entire list are the P values. So I don't need to do P equals, Q equals, and then a list. If your Q equals 1, you can go straight to your list. So that'll be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. So that's the first reason I chose this example, just to highlight that fact. So let's go ahead and synthetically divide. 1, -5, -5, 23, 4, and 10. Again, for our notes, I would hold off until we guess correctly. Just give me a number from that list. -5 I heard. 1, -5, -10, +50, 45. See how it's getting really, really big? So I'm guessing -5 is not going to work. Try again. -2 I heard. So 1, -2, -7, 14. That's going to be a 9. That's going to be -18. That's going to be a 5, -10, 0. Hey, -2 works. Yeah. So the problem always, the synthetic division always reduces by one exponent. So this is x cubed, x squared, x and constant. So it's a cubic function. It's still pretty big, but I got 4 terms. Hey, I can try to factor. But gosh darn it, if you try factor by grouping, nothing I can pull out. So here we are. This is the second reason why I chose this example. I'm stuck. This is, quote, not factorable. So when I'm stuck at a, quote, not factorable situation, P's and Q's again. So the moral of the story, the reason why I picked this as an example, you may have to do P's and Q's more than once in a problem. But again, your Q number, here's Q, here's P. Your Q number is 1, so you can go straight to your list. My list is ±1, ±5. Also, any number that did not work, you can carry them over. So when I do synthetic division a second time, 1, -7, 9, 5, I know I do not have to guess -5 because we've already ruled them out. So give me guess another number from this list. 1 I heard. Ooh.
Wait, if -5 isn't 1, then why 20?
Just because out of that's the process. Yeah. Force of habit. So you guys guessed 1, 1, 1, -6, -6, 3. So that's not going to work. So 1 doesn't work. -5 we've already ruled out.
Oh, yeah.
+2.
2's not on the list.
Negative one.
-1. The only other number, guys. Come on. So 1, -1. Actually, no. There's actually another answer. -8. That's an 8. So that's not going to work. So -5 is the last one that we need to try. 1. Oh, +5. 1, 5, -2, -10, -1, -5, 0. There we go. So then this reduces to a quadratic. The moment you reach an x squared, you can stop the P's and Q's business because we have tools to handle quadratics. You can factor, you can complete the square, you can do quadratic formula. The original instructions said find the zeros, so I got to set it equal to 0 and solve. So the third reason why I chose this example, I got a quadratic. He's not factorable. So you always have completing the square or quadratic formula in your back pocket. You guys, I know a lot of you guys like quadratic formula. Feel free to do that in your notes. In my notes, I'll show completing the square because that's what I like. So I'm going to add 1 to both sides to leave a gap here. I got to fill that gap with something. It's half of this number squared. Half of 2 is 1. 1 squared is 1. So you add 1 to both sides. The left-hand side is now factorable, so that's x minus 1 quantity squared equals 2. You take the square root. X minus 1 equals, when we take a square root to solve, you get a plus or minus. And then one last step is just to add a 1. Again, please don't make this mistake. You're so eager and anxious. Hey, I solved it. I'm going to circle it and move on. That's only the solutions to the quadratic. We need to include the solutions that we guessed correctly. So your complete answer would be 1 plus or minus radical 2, -2, and 5. Right? Those are the answers to the original function. So P's and Q's, it's a great theorem to use if you have a, quote, not factorable polynomial. You may have to use P's and Q's more than once. If your Q value is 1, your entire list are the P values. And the moment you hit a quadratic, you can stop anything special. Just use good old-fashioned solving. Okie dokie? That's it. That's all 3-4 is. A fun way to solve polynomials.
That was way much better than yesterday.